So hi, we are here to present the official case study at Flowmeter Solutions. I'm Ashish Reddy and this is my team. So this is Ham, this is Vladimir and this is Hao. So I'll be taking you through the introduction and the FTMS selection part, followed by Vladimir and the others. So yeah, let's start. Thank you. So this is just the introduction of the business, and we'll give you an overview of the Flowmeter Solutions. So Flowmeter Solution is a US subsidiary of the Italian-based Bertoni Group, a worldwide leader in manufacturing bulk solid material handling systems. So the business supports a variety of customer industries, including construction, mining, agriculture, and food processing. The product line include blenders, weight feeders, conveyors, and flow meters. So the product come in two ranges and three configurations. So they have a low range one which is targeted at small and medium manufacturers, and the high range one which is inherited from their from the Bertoni Group. So and three configurations. The first one is the standard configuration, which accounts for about 40% of their units sold. So these are basically catalog products, so only 25% of them require modifications. The second configuration is the configured one, so it also accounts for about 40% of the units sold, and 30% of the 40% require custom configuration. The third configuration is the integrated systems, which account for about 20%. So this involves complete redesigning the system. So they're currently at about 30 million revenue with 170 employees. So these are the current state problems which the business is facing. They have a high lead time and a high non-touch time, which is hurting the business. The current average lead time is about 32 days. So we can also see in the past 2 years, the lead time is increased for about 35%. So there are signs of lead time spiral in the organization. The code success rate is as low as 15% for some parts of the business, and dropping delivery performance below the 90% mark. So due to this, the costs are increasing and the revenue and profits are shrinking. So these are gives the touch and non-touch time for the quoting and the ordering process. As you can see, the non-touch time is very high. For the standard products, it's about the touch time is about 4%, and for the integrated products, it's about 1%. So that's very low. So motivation for our Q-ROC cell. So the first thing we need to do is we need to reduce the lead time for quotation and order processing, and eliminate wasteful and repetitive process which is increasing the lead time basically. So increase success rate of quotations, increase profit margin, and create a spare capacity so it can handle future demands. So these are the four ingredients for the Q-ROC cell. It must be multifunctional, co-located, should be closed loop and cross-trained. And these are the three steps we followed to build our Q-ROC cell. First, we went with choosing the FTMS, then designing the cell, and we had dynamic adjustments of the cell using the MPX software. So this is focus target market segment. So we want to start the Q-ROC effort, as I told you, by looking at a sub-segment of the business where there is an opportunity for success. So the three main factors we chose were revenue, to select the FTMS were revenue, volume, and lead time. So this is the chart, revenue chart. We are not considering the aftermarket products because it's not in the scope of the project. So blenders have contribute about 22% of the annual revenue, about $7 million. Coming next is the conveyors and the flow meters. So this is a graph of the code success rate for each sub-segment. So as you can see, the standard products in general have a very low code success rate. This is due to the high competition in the market. And within the sub-segments, you can see that flow meters and blenders generally have a low code success rate. So the focus target market segment we selected was integrated blenders and integrated flow meters. So first we thought of selecting the standard products as our FTMS because the business is facing a lot of problems with this segment due to a lot of competition in the market. But still we went with integrated products since there is a lot of scope for improvement. And in standard products, the lead time is, I think it's low, so the scope for improvement is lower. So and integrated products, we have the business has already an advantage in this market. So furthering this advantage will give you a big boost in revenue. So as I told you, integrated systems has very high lead time compared to other configurations. In terms of revenue, blenders contribute to about 22% of the total revenue, and also the quote success rate for integrated blenders and flow meters are not so high. So we chose that as the FTMS, and the product we chose was quoting and order processing. So Vladimir will take you over to the process. Thank you.
Thank you, Ashish. All right. So this is the current state process flow just for securing quotes. One of the philosophies of quick response manufacturing is having a system-wide view of what's happening at your company. Oftentimes, quality improvement projects will focus on the improvement of a subsection at the cost of the larger system as a whole. So whatever improvements we make, we ultimately want to improve the company as a whole, not just that specific center or department. So with that in mind, getting a better idea of how the company works as a whole, we'll begin. The way this chart works is you basically follow the arrows. You have groupings, like for example here, you have a grouping for the main office. So all of that occurs here, and then you have sub-departments. Several blocks that are connected refer to perhaps a single person doing multiple jobs, but they follow a different sequence. Let's see. So let's begin. Products start in the field with the customer up here. You set product specifications, performance requirements, and they decide, or they meet with the field representative. So here's our first arrow, right? You do steps 1, 2, and you come to here. There's a request for a quote by the field representative. It's a very critical step securing your sales. Next, that's sent to a customer service office. They create an RFQ folder. What's that?
You can use the pointer.
Pointer, yeah, okay. They create an RFQ folder here. That's sent to Joe. Joe actually does a lot of work, but just for these preliminary products, it's sent to him here. He assigns it to a specific application engineer. Let's see. So next, you have sort of a fork in the road based on your different products. So you have an arrow for standard. We'll start with that, I suppose. Standard is the simplest. They verify specs for the application engineer for a standard product. They verify the specifications, estimates a price. That's sent to production control, which is, I believe, also in the main office. They estimate a delivery date. That's sent back to Joe, so you can see that Joe is doing these several tasks. He signs off on the quote, sends it to the field representative. They receive the quote and approve it, and then they send it back to the customer, back up here. So this is this arrow returning here. So that's your standard product. Next, back to this fork. You have configurated and integrated. They sort of share an early path. That's sent to the main office in engineering first. So they create a mesh spec sheet, then they create an electrical design sheet, and they send the quote to Corey. Corey is a pretty busy person at this company based on what we've seen. Corey reviews the quote, and he assigns mechanical and electrical engineers that he feels are either experienced or qualified for this particular task. That goes here first to mechanical, then to electrical. Both of those departments select components. And then if it's integrated, it's a little bit different. We'll come back to that later. So key electrical components are selected, it moves down here, and it goes to the purchasing department in the main office. They examine their bill of materials, they identify items with the longest lead time, and determine if it's the promised delivery date. One of the things that this company found was that they had to verify vendor lead time. Sometimes that wasn't exactly consistent, so it would vary. Perhaps if that company was really busy, or if we're really busy, the lead times might get bloated. So having a clear understanding of what companies deliver consistently on time and which ones have that variance is really crucial in selecting proper designs and setting a good quote and due date. So that comes here. After that, you send it to production control. They estimate a delivery date. So again, that's contingent on vendor lead times. From production control, it's sent back to Joe, who signs off on the quote, sends it to the field operations operative, your salesperson. They send it to the customer, and then they either win or lose the quote. Last product, which is in our FTMS, would be the integrated products. This is the most complicated product, and that coincides with such a long lead time, that makes sense. So over here, you have a similar process to the configured products, right? But there's a little bit more engineering that goes into it. So it goes through mechanical, through electrical, and then for an integrated product, they send a preliminary design. Rather than sending it directly to purchasing, they actually send it back to Joe, again, Joe. He reviews the preliminary design and then sends it to the field representative to iteratively approve updates with the customer. So the iterations happen between the customer, the field operative, and Joe. This is an iterative process. They meet several times. And if the iteration meets some number or if Joe feels it's appropriate, we'll actually send Joe out into the field to meet with the customer personally on site and try to close that deal. So this is Joe meeting with the client up here. If that's a success, then we're back on sort of the configured track where that comes over here, down here, and then we have the product where the quote sent back to purchasing, where they look at the different components that were selected, they cross-reference it against vendor lead time based on their experience with that vendor, then it's sent to production control, then it's sent back to Joe, he signs off on it, and there you go, then they get the final quote. So there's a little, for integrated products, there's a lot more looping happening in the design process with the customer. All right, so that's just quoting. That's even before you start your, your engineering work for the final product. There we go. Now we have order processing. So again, we have Corey's quite involved and Joe's quite involved in this process. We begin, use the pointer up here. The purchase order for a secured quote is received by the field representative. It's sent to the main office where they enter the order, or customer service representative, and then Joe begins his work again. So he logs that information into the ERP system, he assigns an application engineer to review the product, and then if it's integrated, he'll actually verify the folder for completeness, an important step so that you don't have to meet with the customer again, or if you do that as quickly as possible. Completeness of documentation. And then similar to the quoting process, you have like a fork in the road for different product types. Same as before, we'll start with standard. So standard takes that folder and sends it to the main office for engineering. If it's a standard product, it's reviewed by a standard qualified application engineer. It's sent directly to the main accounting office. They verify credit and sale conditions. From there, it comes in here. The bill of material is finalized, and they prepare the job packet. And then pretty smoothly, it's sent into production control, sent to the shop floor, and then they machine the part and send it off to shipping. Next, for configured products, so a little bit more complicated. Instead of directly reviewing the order, they review the order and they review drawings because it's a more complicated product. After that, it actually gets sent to Corey, who's one of the managers for the different engineering departments. He sends it to the mechanical engineers. Mechanical engineers select components. That's sent to the electrical engineering department. From there, it's sent back to Joe. Joe does some change approval. And then from here, sent to accounting, similar to standard products. That goes to the manufacturing engineers. Then production, and then we're done with configured. Last step, so the integrated products, which is what we'll be looking at, that goes directly to Corey, right? From there, Corey actually does detailed engineering himself. Maybe he gets help from some of his engineers, but that tends to be a much more involved process. And he actually has to work quite closely with the field representative and the customer. The customer then, because it's an integrated product that's customer specific, the customer actually has to follow this arrow over here. They have to work directly with qualified integrated engineers, both in mechanical and electrical. And this is an iterative process between these, I guess you could say, four parties. So it's the customer, field representative, Corey, and the engineers that he picks for the task. So this goes through several iterations. Once that's successful, Corey approves that integrated design, assuming the customer's happy, field representative's happy, sends it to Joe. Joe then sends it to accounting, sends it to manufacturing, sends it to production, you know the drill. And that's the whole process. So in summary, it's a pretty complicated procedure. So let's see. So the people that tend to be fairly highly involved, like key pieces in the puzzle, Joe is very busy. Corey is quite busy because he's sort of the gatekeeper to any sort of engineering work that happens either in the quoting process or in the product development side of things. Same thing with order processing. Corey's really involved, Joe's really involved. Some of the things that I noticed was how the lead time selection or the purchasing looks at lead time for the components selected. Engineers don't, to my knowledge, don't consider lead time until they've already selected like the proper component from an engineering standpoint. And with that, I think I will pass to assumptions for our model, right?
Okay, then we start to build our MPX model. First, we make some assumptions. For the working hours, we assume people only work in the weekdays, and so 8 hours per day. So there is total 2,080 hours per year. And for the employee, the mean time to failure and the mean time to repair will follow the Bernoulli distribution, and 20% of the time is for the mean time to repair, and 80% of the time will be for the mean time to failure. And for the operations, first, as we did before, we extract the operations from the process description, and then we calculate the mean value and variance of each operation based on the touch time and divide it by the number of operations we just got. And then we generate the value for each operation, and during this process we assume the processing time of the operation will follow the normal distribution. And since it's an office operation, we assume the loss size to be 1. And lastly, there are some iterations involved in the process. For the coating process, we assume an average of 4 iterations between Joe, customer, and the field representatives. And here's our Q-ROC design. Basically, we group people who have similar kind of duties into one Q-ROC. And here you can see we basically have 3 Q-ROCs, and the first Q-ROC is for the people who have sales-related jobs, and the department includes accounting, application engineering, and field representative. And the second Q-ROC contains people with engineering-related jobs, and it includes electrical engineering, mechanical engineering, and manufacturing engineering. And the last Q-ROC have the service-related person. It includes customer service, production control, and purchasing. And here is just a reminder: our FTMS is integrated flow meter and blenders. And for the workload per year, we just calculate them based on the sales and request for coating performance. And here's just the advantage of creating the Q-ROC. And then we enter our data to MPX and generate the model. And here, this graph shows the labor utilization. Basically, we get this graph by adjusting the number of employees in each Q-ROC to obtain a reasonable utilization level. We want to make sure the utilization level to be below 75%. And you can see the average here is 63%. And the engineering-related employee has the highest utilization. And here is the graph for lead time and working process inventory. And you can see the lead time for ordering process is like relatively higher than the quoting process. And the average lead time decreased a lot. It's like decreased from more than 100 days to just 10 days after the implementation of Q-ROC. And you can see the average working process inventory is around 1, which makes sense. And now Hao will talk about the dynamic analysis.
Thank you, Hao. So based on our Q-ROC implementation, so we could have multiple dynamic analysis. So the first one is after the Q-ROC implementation, we are assuming that we could have larger quote success rate. And we assume that before the, we assume that after the Q-ROC implementation, the quote success rate would be 52.5%, which is the average value of all the integrated products. And we could recalculate the demand for the order and the demand for the quote. After that, we can just input those values into the MPX model. We could find the lead time has a smaller decrement, and the lead time is around 10 days for the order. The lead time for the quote is around 5 days for the quote, and the labor utilization is around 55%. So we could have some observations from this figure. You can see that in the lead time figure, the larger part for the lead time is about the waiting time for equipment, and we want to verify that our Q-ROC has enough spell capacity to handle so much workload. So in the next dynamic analysis, we'll just assume after the Q-ROC implementation, the order demand will be increased by 20%. And we need to recalculate the quantity for the quote and quantity for the order. So before the Q-ROC implementation, our orders is 13 for flow meters and 22 by blenders. So we just use the 20% increment, then we got the new order quantities, 16 flow meters and 26 blenders. Then we just use these numbers to divide it by the quote success rate, we just get the new quote. So you can see that after this dynamic analysis, our workload compared with before has a 25% increment. So we could just input those values into the MPX model. We get our new lead time and labor utilization. Here you could say the larger part for the lead time is waiting for equipment. And that makes sense because our labor utilization is higher than before. But even though with that higher workload, we can say the labor still have enough capacity to handle that amount of workload. So after implementation, the average lead time is 18.90 days. The average utilization is about around 74%. Let's have a summary of the analysis. So we have 4 experiments here. The red one is about the static one, which we just grabbed data from the data set. And the blue one is just after we got the Q-ROC implementation. So we have 3 employees in 1 Q-ROC, and that would have the lead time around 9 days. So the yellow one is we just increase the quote success rate. That means we have less demand than before. So it will definitely have a lower lead time than before. The green one is we just increase the demand by 20%. That means our labor utilization will be higher than before and lead time will be a little bit higher than before. So based on those summary, we could have 2 significant observations. The first one is the Q-ROC has significant effect on lead time reduction. So comparing with the static one, almost 200 days of the quote and 60 days of the, 200 days of order and 60 days of the quote, we have almost 92% reduction. This is the first observation. The second one is even though we with more demand, that means the fourth, the green one, we have more demand than before. The Q-ROC still has enough capacity to handle that amount of workload. That means our Q-ROC design is good enough to handle all the workload. So later on, Vladimir will just explain the proposed design of the process.
Thank you. All right. So yeah, 92% improvement is nice. So intuitively you'd be thinking, oh, we have to do some major crazy changes. It isn't going to add unnecessary complexity. In fact, it should make your process a lot simpler. Here is the proposed process flow for the quote process. So this is much more straightforward than the previous slide I showed on quote processing. This is achieved through combining processes and fewer handoffs. So same as before, you begin with product specifications from your customer right here. That's reviewed by your sales-related employee, like we mentioned before, somebody cross-trained who has a pretty rich skill set. They review the specification, they create that mesh spec sheet and electrical design sheet. Then they send it to an engineering-related employee. So they work on, what's different is they still work on the preliminary design and they select parts, but we emphasize that they should have a shared database with the purchasing department such that rather than selecting components and then maybe getting not approved by the purchasing department due to long lead times, they should select their components knowing what the lead times are for those components, right? And then pick with MCT in mind, or mean critical path time considerations. So with that complete, they send the design, so that's approved by the sales employee. After that, it's sent to purchasing, and the related items are assigned a due date. And what's nice is that if they work with those purchasing considerations in the early stages of engineering, it's less likely that they'll have to do any sort of rework for the quote, and your quote lead times will diminish a lot. Fewer handoffs, less confusion, and less chaos, all great things. So next, with increased quote success rate, move on to the next. Again, this is intended to be simplified, but you have to have cross-trained employees working well together. So same as before, it starts out in the field. The customer has to approve the order that they accept a quote for. The sales employee verifies completeness with the customer. So this is something that Joe used to do. Next, that's sent to the service people. So another cross-trained employee in our Q-ROC cell. This occurs in purchasing. So they review the price, they check the lead time. The lead time should check out because engineers should be designing with that in mind. If a component is something that they don't use that frequency, they don't know the lead time for, it's okay to have to iterate in that process, but generally this should be like smooth sailing. The lead times should be pretty well done, and approval should be more consistent. So from there, it's sent to engineering. Engineering creates the job packet and releases it to production. And with that, next, pass it to Ashish for financial analysis.
Thank you, Vladimir. So this is a financial analysis. So it's basically not a financial analysis because we were not able to estimate the exact dollar amount for the benefits and costs. So we have listed down the benefits and costs incurred by the company, but we recommend the business to measure all the areas which affects the cell and come up with the financial analysis. So this is just a list. So benefits of the Q-ROC cell. So we have reduced lead time of the cell by about 90%. So process redesign saves time of labor and cost. So increase in code success rate because of the lesser lead time. So the Q-ROC promotes continuous process improvement, and we can see there's an increase in profits and revenue. So but the costs incurred are costs due to the cross-training operators, relocation of the office, utilities, furniture, additional IT support, and Q-ROC training and consultancy. So the last slide is our recommendations. So the first step is to implement the Q-ROC cell with the FTMS of integrated flow meters and integrated blenders. Then process redesign. So eliminate handoffs and intellectual setups and iterative steps. So eliminating authorization and checks between functional departments, and cross training. So we had one Q-ROC cell and 3 sets of employees, like one trained in sales, the other in engineering and service related activities. So data collection of data related to cell and verify the impact of the cell and promote continuous process improvement. And the organization structure we propose should be individual ownership within cell and responsibility and authority for decision making. Yeah, thank you.